So we're going to talk about the complex capacitor combinations. So the capacitors this time are not connected purely in series nor connected purely in parallel. So this kind of combinations of capacitors, some capacitors are connected in series while some capacitors are connected in parallel in one circuit. Or capacitors that are connected in series are connected parallel to the other capacitors, or capacitors that are connected in parallel are connected series to the other capacitors. Okay, so this is what we call the complex capacitor combination. So there is series combination and there is also parallel combination in one circuit. So like determining the voltage across each capacitor, or the charge per capacitor, the total charge, and the equivalent capacitance of the circuit, we can still obtain or determine the capacitor, the equivalent capacitance, the voltage differences, and then the total charge by following these steps. Okay. First is to combine capacitors that are in series or in parallel, and then the next is to derive the formula. We know already what is the equivalent capacitance if they are connected in series, and then we know already that what is the equivalent capacitance if they are combined in parallel or connected in parallel. Okay? Then you know already what we call the equivalent capacitance. Okay? So we can combine the capacitors that in series, and then we have one capacitor. Then the capacitance of that imaginary one capacitor is what we call the equivalent capacitance. And next is to redraw the circuit after every combination. Okay, so we redraw. So from three capacitors, we can redraw that into one capacitor. And then next, we need to repeat the first two steps until there is only single equivalent capacitor. And then next is to find the charge on the single equivalent capacitor using the equation, the capacitance equals charge, total charge per voltage. And then we need to work backwards through the diagrams to the original one, finding the charge and voltage drop across each capacitor along the way. So to do this, we need to use the following collection of facts. The capacitor equation. First, the capacitor equation, we have the capacitance equals charge per voltage. Next is the equivalent capacitance if capacitors are connected in parallel. And then the equivalent capacitance if they are connected in series, it's letter D. And then for letter C, capacitors in parallel all have the same voltage difference, right? As does their equivalent capacitor. Okay. Next, capacitors in series have the same charge Q as does their equivalent capacitor. So let us have example number 1 where the capacitors are connected in series while they are connected while those capacitors that are connected in series are also connected parallel to the other capacitors. So like this one. So this is an example of capacitors or complex combination of capacitor. Okay. So these two capacitors, C3 and C4, are in series connection. Like because the negative terminal of the negative plate of C3 is connected to the positive plate of C4. So it means these two capacitors are connected in series. For C1 and C2, these two capacitors are connected in series since the negative plate of C1 is connected to the positive plate of C2. But we are going to combine these C3 and C4. The combination capacitor of C3 and C4 is parallel to the combination of C1 and C2. Okay. So we will obtain the voltage across each capacitor, the voltage across C3, C4, C1, and C2, and then we will determine the charge of every capacitor and the total charge and the equivalent capacitor or capacitance of this circuit. So what is the first thing to do? We need to combine capacitors that are in series or in parallel. So these two capacitors are connected in series. C3 and C4 are connected in series. C1 and C2 are connected in series. So we can combine 3 and 4. Okay? And C1 and C2 into one capacitor like this one. Alright? Since capacitor 3 and capacitor 4 are connected in series, then the equivalent capacitance of C34 is the combination of capacitor 3 and capacitor 3 and capacitor 4. So we can combine that into C34. Since C3 and C4 are connected in series, then the equivalent capacitance or the reciprocal equivalent capacitance of C34 is equal to the 1 over capacitance of 3 plus 1 over the capacitance of 4. Okay. Next, 1 and 2 are in series connection. So we can combine that into 1. Then we have C12 as the combination of capacitor 1 and capacitor 2. So what is the equivalent capacitance of C12? Since capacitor 1 and capacitor 2 are connected in series, so this is the equivalent capacitance. 1 over C12 is equal to 1 over C1 plus 1 over C2. Okay? But we can still simplify this circuit into 1 since the combination of capacitor 3 and 4 is parallel to the combination capacitor of 1 and 2. So we can still redraw this circuit into most simplified circuit into CEQ. Alright? CEQ means this is the combination of C12 and C34. So you can see C34 and C12 are parallel. These two capacitors are connected in parallel. Then this is the combination. The equivalent capacitance is CEQ plus C12 plus C34. Okay? So since this is the equivalent capacitance if they are connected in parallel. So let us determine the voltage across each capacitor as well as the charge per capacitor, the total charge, the equivalent capacitance and the equivalent capacitance. So we can simplify this circuit into C34. 3 and 4 are in series, so this is in series. C12, so C12 are in series connection, and then we can still simplify this circuit diagram into 1 since 3, 4 and C12 are connected in parallel. So this is the most simplified circuit diagram. Alright, so first step is to combine the capacitors. We're done with that, and then withdraw already. And then next, we need to repeat the first two steps until there is only one single equivalent capacitor. We are done, and then we'll find the charge on the single equivalent capacitor using C equals QV. Alright, so let us start first for C3 and C4. Since they are connected in series, then what is the equivalent capacitance of C34? So that's 1. That's 1. So that's 1 over C34 must be equal to 1 over C3 plus 1 over C4 since these two capacitors are connected in series. So what is C3? That's 1 over 3 microfarad plus 1 over C4 is 6 microfarad, so 6 microfarad, and that is 1 over 2 microfarad, or C34 equals 2 microfarad. That's C34, right? Next is C12. C12, capacitor 1 and capacitor 2 are connected in series. Then we have 1 over C12, since this is these two capacitors. Alright, this is 1, 1, 2. Two capacitors are connected in series, so the equivalent capacitance of C12 must be equal to 1 over C1 plus 1 over C2. Then what is 1 over C1? That's 1 over capacitor 1 is 2 microfarad plus C2 is 1 over microfarad. So that's 1 over 4 microfarad. We have 3 over 4 microfarad. That's 1 over C12. Or C12 equals 4 over 3 microfarad. Okay, so we have C12. So next, we will work on this diagram. Okay, so CEQ is the combination of C34 and C12. Since C34 and C12 are connected in parallel, so the equivalent capacitance must be C12 plus C34, right? So the equivalent capacitance CEQ equals C12 plus C3. Cannot be seen. So let's move. So the equivalent capacitance equals C12 plus C34, right? So next, what is C12? That's 4 over 3 microfarad. That's 4 over 3 microfarad. Right. Plus C34. What is C34? C34 is 2 microfarad. Then the equivalent capacitance must be equal to, so that's 10 over 3, I think. Multiply it by 3, 6 over 3, that's 2, 6 plus 4, 10. Okay, so they have 10 over 3 microfarad. So we have the equivalent capacitance. Alright. What is equal? What is this saying? If capacitors are connected in parallel, the voltage across each capacitor are the same. Voltages are the same if capacitors are connected in parallel. So it means since C34 and C12 are connected in parallel, then the voltage across 34 must be equal to this one, 90 volts. Okay. So C12 is also, or V12, the voltage across C12 must be also equal to 90 volts, right? So what is the equivalent so next is the charge, okay, the total charge. Since capacitance, equivalent capacitance is total charge over total voltage, then the total charge must be equal to the equivalent capacitance times the total voltage. What's the total capacitance? That's 10 over 3 times 10 to negative 6 farad, since this is microfarad, multiplied by the total voltage of the circuit, which is 90 volts. 90 volts, right? So the total charge would be equal to 3 times 10 to negative 4 coulomb. Please double check using calculator. Okay, so that's the total charge. Next, we will obtain the charge of C34. Alright, so the charge of C34 or Q34 will be equal to the charge, the capacitance of 34 times the voltage of 34. Do we have the capacitance of 34? Equivalent capacitance of 3 and 4? Yes, we have, which is 2 microfarad. So this is 2 times 10 to negative 6 farad multiplied by the voltage across 34, which is 90 volts. 90 volts. Okay, so we have so the charge of 3,4, is 1.8 times 10 to negative 4 coulomb. So since 3 and 4 are connected in series, so what is equal for every capacitor if capacitors are connected in series? The charge. Okay, so the charge is equal, the equivalent charge of 3,4 is equal to the charge of 3 as well as the charge of 4. So meaning Q3 equals 1.8 times 10 to negative 4. Okay, Q4. Then Q4 is also equal to 1.8 times 10 to negative 4. Alright, next is the charge combination charge of 1, 2. So charge 1, 2 must be equal to the capacitance, equivalent capacitance of 1, 2, the voltage across 1, 2. What is the capacitance 1, 2? Where is it? Yeah, this is 4 over 3 microfarad, or that's 4 over 3 times 10 to negative 6 farad times the voltage across 1, 2. Where is voltage across 1, 2? That's 90 volts. And we have times 90 volts. Okay, and that is equal to 1.2 times 10 to negative 4 coulomb. Okay, since C1 and C2 are connected in series, so what is equal for every capacitor? That is the charge. So the charge 1, 2 is equal to the charge 1 and charge 2. Right? So Q1 equals 1.2 times 10 to negative 4 coulomb, and Q2 is also 1.2 times 10 to negative 4 coulomb. So this time, we're going to determine the voltage across each capacitor. So let us start at the voltage 1, or the voltage across resistor 1. So since C equals Q over V, then V equals Q over C, then V1 should be equal to Q1, charge of 1, over capacitance 1. Okay, so what is the charge of 1? Do we have charge of 1? Yes, we have 1.2 times 10 to negative 4 coulomb over C1, capacitance 1. Where is capacitance 1? Which is given already. Okay, capacitance 1 is 2 microfarad. So this is 2 times 10 to negative 6 farad. So V1 is 60 volts. So that's V1. Next, V2. So V2 is Q1 over C, Q2 over C2. And then what is Q2? Do you have charge at capacitor 2? Yes, that's 1.2. So this is 1.2 times 10 to negative 4 coulomb over the charge of 2. What is the charge of 2? That is 4 microfarad. So that's 4 times 10 to negative 6 farad. Okay, then we have then V2 is 30 volts. How about V3? V3 is Q3 over C3. Q3, do we have Q3? Yes, which is 1.8. This is 1.8 times 10 to negative 4 coulomb over capacitance 3, which is 3 microfarad. So that's 3 times 10 to the power negative 6 farad. Then Q3 equals then V3 is 60 volts. Okay. V3 is 60 volts. Next, V4. V4 is Q4 over C4. What is Q4? Do you have Q4? Yes, which is 1.8 times 10 to negative 4 coulomb. Sorry, I forgot to put the unit here. C is for coulomb. So Q4 is 1.8 times 10 to negative 4 coulomb over what is C3? C4. C4 is 6 microfarad, or 6 times 10 to negative 6 farad. Then V4 equals V4 is 30 volts. So do we have Q1, Q2, Q3, Q4, the total charge, okay? Then we have V1, V2, V3, and V4, and total voltage is already given. And we have the equivalent capacitance. Okay? So that's example number 1. Next, example number 2, where there is complex combination of capacitors. So as you can see in the diagram, okay, there are capacitors that are connected in series, and there are capacitors that are connected in parallel. So as you can see, C1 and 2 are connected in series, while 3, 4 are connected in parallel. And C3 and C4 are connected parallel to the combination of C1 and C2. So, first step is to combine all capacitors that are connected in series or connected in parallel, and I will simplify the circuit diagram. So, to simplify this, we will first combine C1 and C2 because they are connected in series. Then we have C12, and C12 is connected parallel to C3 as well as capacitor 4. And then we can still simplify this into the most simplified circuit diagram, where C1, 2, C3, and C4 are combined as 1 or reduced as 1. Then we have the equivalent capacitance. Alright? So, let us first obtain the equivalent capacitance of C12, because we cannot obtain CEQ if we don't know the C12. Since C12 are connected in series, then the reciprocal capacitance, equivalent capacitance of 12 must be equal to the sum of the reciprocal capacitance of each capacitor. So that's C1 and C2. So let's obtain first C12. So C12 must be equal to 1 over C1 plus 1 over C2, since C1 and C2 are connected in series. So what's 1 over C1? That's 1 over 24 microfarad. So that's 1 over 24 microfarad plus C2. C2 is 8 microfarad. So that's 1 over 8 microfarad. Then 1 over C2, 1 over 6 microfarad, or C12 is 6 microfarad. 1 over C12 is 1 over 6 microfarad. So C12 is 6 microfarad. So we have C12, and C3 and C4 are given. Capacitance of 3 and capacitance 4 are given. So we can now obtain the equivalent capacitance, which is the combination of 1, 2, 3, and 4. Okay? So since C1 to C3 and C4 are connected in parallel, then the equivalent capacitance CEQ must be equal to C12 plus C3 plus C4. Right, C3 and C4. And what is C12? We have 6 microfarad. So this is 6 microfarad plus C3. Well, this C3. C3 is 2 microfarad. Okay, so plus 2 microfarad plus C4, which is 4 microfarad. Then the equivalent capacitance is just 12 microfarad. So we have the equivalent capacitance. Next, the total voltage is given already, which is 36 volts. Next is the total charge of the circuit. The total charge, or the charge of the equivalent capacitance. Alright. So since capacitance equals charge over voltage, then total charge must be equal to the equivalent capacitance times the total voltage. Equivalent capacitance is 12 microfarad, or 12 times 10 to negative 6 farad, multiplied by the total voltage is 36 volts. Then the total charge will be equal to 4.32 times 10 to negative 4 coulomb. Right? So next is the voltage across resistor. Since C1, 2, C3, and C4 are connected in parallel, so what is equal for every capacitor? That is the voltage differences. Okay, all voltage differences are equal since they are connected in parallel. So C12 or V12, V12 since the voltage difference. V12 equals the total volts is 36 volts, so this is also 36 volts. And C3, the voltage across C3 is still 36 volts. And then the voltage across 4 is still V4 equals 36 volts. Okay, so we have V3 and V4. Alright, so next, what is the voltage across 1, 2? Okay, we cannot obtain that because we don't have Q1 and Q2. Okay, so let us obtain first the charge of capacitor 3 and charge of capacitor 4, since we have V3 and C3, and for V4 we have Q4 and C4. V4 and C4. So we have Q3, since capacitance equals charge over voltage, then that's capacitance 3 over voltage across capacitor 3. Capacitance 3 is 2 microfarad, or 2 times 10 to negative 6 farad, times voltage 3, which is 36 volts. Okay, so that is equal to the charge of 3 is 7.2 times 10 to negative 5 coulomb. Right. Next is Q4. Q4 is C4 times voltage across C4. C4, what is C4? That is 4 microfarad, or 4 times 10 to negative 6 farad, multiplied by V4. V4 is 36 volts. So 36 volts. Okay, so Q4 equals 1.44 times 10 to negative 4 coulomb. That's Q4. Okay. Next, since we don't have Q1 and Q2, we'll obtain first Q1, Q2. So Q1, Q12 is C12 times V12. Right? What is C12? C12 is 6 microfarad or 6 times 10 to negative 6 farad multiplied by V12. V12 is 36 volts. Then we have Q12 equals 2.16 times 10 to negative 4 coulomb. Okay, that's Q2, Q12. Now, since, let's go back. So, since C1 and C2 are connected in series, so what is equal in 1 and 2? They must have equal charge, right? Since they are connected in series. But the total charge of 1 and 2 is 2.16. So, the total charge must be equal to the charge of C1 and must be equal to the charge of C2, right? So Q1 must be equal to 2.16. Q1 must be equal to 2.16 times 10 to negative 4 coulomb, and then Q2 is also 2.16 times 10 to negative 4 coulomb. Okay, so we have Q1 and Q2, right? We don't have the voltage across 1. We don't have voltage across 2. So we can obtain, since we have the charge of 1 and charge of 2. So what is V1? Okay, V1 is charge 1 over capacitance 1. What is the charge of 1? 2.16 times 10 to negative 4 coulomb over charge of 1 is 24 times 10 to negative 6 farad, then that is equal to 9 volts. Right. How about V2? V2 is Q2 over C2. Q2 is 2.16 times 10 to the power of negative 4 coulomb over C2, what is C2? 8 microfarad or 8 times 10 to negative 6 farad. So V2 is 27 volts. Okay. So we have V1, V2, V3, and V4. We have Q1, Q2, Q3, and Q4. The total charge and the equivalent capacitance. Right? So that is example number 2. So this is the next example of complex combinations of capacitors. So this is more complicated compared to the previous example, example 1 and example 2. As you can see in the diagram or the circuit diagram, C1 and 2 are connected in parallel. Parallel. And then C5, 6, and 7 are also connected in parallel. We will combine C1 and C2 as one. Then that is C12. And C12 is in series of C4. Okay, again C12 is in series of C4. So you have C4. Okay, so we simplify the circuit diagram. And then 5, 6, and 7 are parallel to each other. Then we can simplify that into one capacitor. We have C5, 6, 7. Okay, C5, 6, 7. The combination of C5, C6, and C7. Okay, and then next, C3 is in parallel with C5, 6, 7. So we can still simplify this circuit diagram. So this is more simplified circuit diagram, right? So since C1, 2, and 4 are connected in series, then we have combination of C1, 2, and 4 is C1, 2, 4, right? And C3 and C5, 6, 7, we will combine that C3 and C5, 6, 7 into 1. So you have C3, 5, 6, 7. And then we can still simplify this to have one capacitor and to have equivalent capacitance. Alright, what is this CEQ? CEQ is the combination of C12 and C3567. So again, we'll start at C12. C1 and C2 are connected in parallel, and then the combination of 1 and 2 is in series with C4, and then we'll combine 5, 6, 7. So since these three capacitors are in parallel, okay, so the combination of 5, 6, and 7 is in series with C3. Okay, next, so this is the more simplified. So we'll combine 1, 2, and C4 to 1. We have C1, 2, 4. C1, 2 is in series of C4. And then C3, we'll combine C3 and C5, 6 into 1. Then we have C3, 5, 6, 7. C3 and C5, 6, 7 are in series connection. And C1, 2, 4 and C3, 5, 6, 7 are parallel. Then we have the equivalent capacitance. So this is the voltage. So let's go back to the first simplification of the circuit diagram. So since C1, 2 are connected in parallel, then what is the equivalent capacitance of C1, 2? Okay, since they are parallel, then we have, where will I write? Here, C1, 2 equals C1 plus C2. Okay, C1, 2 equals C1 plus C2. What is C1? 5 microfarad. And what is C2? C2 is 4 microfarad. Then C1, 2 is 9 microfarad. It's 9 microfarad. C1, 2. Next, okay, the combination. So let us combine C1, 2 and C4. So they are in series connection. C1, 2 and C4 are in series connection. Then 1 for the equivalent capacitance of C124 or 1 over C124. Since C12 and C4 are connected in series, so that is 1 over C12 plus 1 over C4. Alright, C4. Then what is 1 over C12? That's 1 over 9 microfarad plus 1 over C4. What is C4? That's 3 microfarad. 1 over 3 microfarad. And that is 4 over 9 microfarad. Or C12 equals 9 over 4 microfarad. Okay, next. So you have C1, 2, 3, C1, 2, 4. How about the combination of the C5, C6, and C7? C5, C6, and C7 are parallel to each other. Then the equivalent capacitance of C5, 6, 7 must be equal to C5 plus C6 plus C7. What is C5? That's 2 microfarad plus C6 is 3 microfarad plus C7, that's 7 microfarad. Then C5, 6, 7 equal to C5, 6, 7 equal to what's 2 plus 7, 9. Then we have 12 microfarad. It's 12 microfarad. So we have the combination of 1, 2, 4. Yeah, this is 1, 2, 4. Then we have C5, 6, C5, 6, 7. Alright. How about the C3, 5, 6, 7? Okay, as you can see, C3 and combination of 5, 6, and 7 are in series. Then C3567 must be equal to 1 over C3 plus 1 over C567. Okay? And 1 over, what is C3? That's 6 microfarad. Plus 1 over what's C567? That's 12 microfarad. So this is 12 microfarad. Then that is multiplied by 2. That's 3 over 12 microfarad. Or C3567 must be equal to 4 microfarad. Okay, so we have C3, C5, and C7. Then we can obtain, the equivalent capacitance. Equivalent capacitance is the combination of C124 and C3567. Right? 1, 2, and 3567 are parallel. Then the equivalent capacitance, which is equal to C124 plus, since they are parallel, plus C3567. Okay. C124 is 9. I know, 9 over 4. Okay. 9 over 4 microfarad plus C3567 is 4 microfarad. 4 microfarad. So that is, this is multiplied by 4. 16 plus 9, that's 25 over 4 microfarad. So that is the equivalent capacitance. Right? We have now the equivalent capacitance. Since C12 and C356 are connected in parallel, then C12 will experience the same voltage across its capacitor, the same or equivalent to the total voltage, which is 48 volts. Also, C3567 will experience the same amount of voltage across each capacitor, which is 48 volts. So V1 to 4 is 48 volts. Then V3567 is also 48 volts. Alright, so let's go back to this one. Alright, so since C12 and C4 are connected in series, so C12 will experience the same amount of charge, of C4. But what is this C4? Okay, we don't know. We still have to get the charge of C124. So what's the charge of C124? Charge of C124 is equivalent capacitance of 124 and voltage 124. And what is C124? We have 9 over 4 microfarad. So this is 9 over 4 times 10 to negative 6 farad multiply by voltage, okay, voltage of V124, which is 48 volts, okay, 48 volts. Then Q124 equals 1.08 times 10 to negative 4 coulomb. So since C124 is combination of C12 and C4, and C12, C4 are connected in series, so it means C12 will experience the same magnitude of charge of C4, which is equivalent to the charge Q124. So we have charge Q124, which is 1.08 times 10 to negative 4th coulomb. So Q4, which is charge of 4, capacitor 4, will also be equal to 1.08 times 10 to negative 4 coulomb. Right? We have Q4. Okay, next we have the Q12 is also 1.08 times 10 to negative 4. So we have Q12. How about the voltage across C12? The voltage across C12, since we have Q12, we also have C12, so we can obtain V12 here. So V12 equals Q12 over C12. Then what is Q12? What is Q12? 1.08 times 10 to negative 4 coulomb. Okay. So divided by C12 is 9 microfarad. Or 9 times 10, power of 6 farad. V12 equals 12 volts. V12 is 12 volts. So let's go back to the original circuit diagram. 1 and 2, C1 and C2 are connected in parallel. So what is equal? The voltage, the equivalent voltage of C1 and C2. What's the equivalent voltage of C1 and C2, which is V12, so 12 volts. So it means V1 also experience a 12 volts as well as V2. Alright, so we have V1 and V2. Alright, so they have Q1 and Q2. We don't have Q1 and Q2. So let us solve for Q1 and Q2. So Q1, what is Q1? Q1 is C1 times V1. What is C1? 5. Let's see. What is C1? C1 is 5 microfarad. So this is 5 microfarad multiplied by voltage across 1, which is 12 volts. 12 microfarad is 5 times 10 to negative 6 farad. Then Q1 is 6 times 10 to negative 5. It's Q1 coulomb. Right. How about Q2? Q2 is C2 times V2. Do you have C2? Yes. That's 4 microfarad. So 4 times 10 to negative 6 farad multiplied by what is V2? 12 volts. Okay, 12 volts. Then 2 is 4.8 times 10 to negative 5 coulomb. Alright, so we have Q1, so we have Q1, Q2, and Q4. Q3, how about Q3? We don't have Q3, but we have V1, V3, 5, 6, 7, right? But we don't have V3, 5, 6, Q3, 5, 6, 7. So we need to look first for Q3, 5, 6, 7. Okay, so this is the Q3, 5, 6, 7, which is equal to C3, 5, 6, 7 times voltage of 3, 5, 6, 7. Okay, so what is the voltage of 3, 5, 6, 7? What is the capacitance of 3, 5, 6, 7? It's 12 volts, so that's 12 times 10 to negative 6 farad multiplied by the voltage across, or the equivalent voltage of this equivalent capacitance of 3, 5, 6, 7. Voltage 48 volts. 48 volts. So Q3, 5, 6, 7 equals 5.76 times 10 to negative 4 coulomb. Alright, since C3 and C567 are connected in series, so the equivalent charge of C3567 will experience by C3 as well as C567. Okay, so meaning Q3 will also experience a charge with magnitude 5.76 times 10 to negative 4 coulomb, and Q567 will also experience 5.76 times 10 to negative 4 coulomb. So next, so I need to list all values of quantities. So since I don't have enough space here, so let us continue. Next, the voltage across 6 and across 7. Okay, but the combination, what is the voltage combination of 5, 6, 7? We don't have V567, right? We don't have V567, but we have Q567 and we have C567. So we can obtain the V of 5. We can obtain the voltage of 567 since we have Q567, this one, and we also have the C567. Alright, so the V, so the V, will I write? So V of 567 must be equal to the charge of 567 over the C567. Right, what is Q567? Where are you? Q567 is 5.76 times 10 to negative 4 coulomb over C567. Where are you? C567, that's 12 times 10 to negative 6 farad. Then the voltage, the equivalent voltage of 567 is equal to 48 volts. Alright, 48 volts, and look at the diagram. The equivalent voltage of 567 is 48 volts. C5, C6 are connected in parallel, right? So meaning C5 will experience the same amount of volts, the equivalent voltage of 567, which is 48 volts. So C6 or V6 is also 48 volts, and V7 is also 48 volts. So we have V5 equals 48 volts. V6 is also 48 volts, and V7 is also 48 volts. Okay, so we can solve for Q5 since we already have V5, V6 and V7. So we can obtain the charge of 5, 6 and 7. Okay, so Q5, what is Q5? That is C5 times V5. What is C5? Okay, let us see the diagram. What is C5? C5 is 2 microfarad. Then this is 2 times 10 to negative 6 farad multiply by 48 volts. Okay, so Q5 equals 9.6 times 10 to negative 5 coulomb. Alright, next we can solve for Q6. Q6 is C6 V6. What is C6? C6 is 3 microfarad, or that's 3 times 10 to negative 6 farad multiplied by V6 is 48 volts. Then that is 1.44 times 10 to negative 4 coulomb. So we have Q6. Okay, next is the Q7, the charge of capacitor 7, which is capacitance 7, voltage across capacitor 7, which is V7. C7, can you see the given? C7 is 7 microfarad. So this is 7 times 10 to negative 6 farad multiplied by V7, which is 48 volts. Then that is 3.36 times 10 to negative 4 coulomb. So that's 3.36 times 10 to negative 4 coulomb. Right? So you have Q6, Q7, and Q5. So next is V3. Since we don't have V3, V3 or the voltage across capacitor 3, we don't have V3. Alright, so V3 is Q3 over C3. So what is Q3? We have Q3, which is 5.76 times 10 to negative 4 coulomb over the capacitance of capacitor 3. Okay, it's given. Capacitor 3 is 6 microfarad. So this is 6 times 10 to negative 6 farad. Then V3 equals 96 volts. Okay, so that's V3. Next is V4. We don't have V4. Alright, so we look for V4. So V4 is Q4 over C4. What is Q4? Q4, where are you? Okay, Q4 is 1.08 times 10 to negative 4 coulomb over C4. Can we see what is C4? C4 is 3 microfarad. Double check. C4 is 3 microfarad. Okay, so this is over 3 times 10 to negative 6 farad. Then V4 is 36 volts. And what is missing? We have Q1 already, Q2, Q3. We have Q4. We have Q5 and Q6. We also have Q7. The total charge. Total charge Q is the equivalent capacitance multiplied by the voltage, total voltage. So it's the total equivalent capacitance 25 over 4 microfarad. So this is 25 over 4 times 10 to negative 6 farad multiplied by the total voltage. Let us see what's the total voltage. The total voltage is 48 volts. Okay, 48 volts. We have 48 volts. Right. So the total charge is 3 times 10 to negative 4 coulomb. So this is the total charge, 3 times 10 to negative 4 coulomb. Right? Okay, so let us check what is missing. So let's start for the charge of every capacitor. So there are 7 capacitors. So there are 7 capacitors. Then it should have 7 charges. Okay. So we start at Q1. We have Q1. We have Q2, right? Then you have Q3. We're done with Q3. Next is Q4. Where are you? Q4. Okay, we have Q4. Next is Q5. Alright, we have Q5. We have Q6. And then we have Q7. Alright. And the total charge, 3 times 10 to negative 4. Next is the voltage across each capacitor. So we start at V1. Where are you? V1, 12 volts. V2, 12 volts. V3, 96 volts. V4, 36 volts. Okay? Then V5, 48 volts. V6, 48 volts. V7, 48 volts. Okay? Total voltage is 48. So it's already given. Next is the equivalent capacitance. Do you have equivalent capacitance? Yes, it's 25/4 microfarad. So we're done. So that is example, the last example of complex combination of capacitors.